So today is going to be a pretty important day. We're going to be looking at how all the things we've learned fit together to allow us to analyze things that are moving vertically. So I'd like to start out showing you all the equations we've learned so far. Most recently, we learned Newton's second law, which is the most important equation of the year. It links together everything else we've done. Before that, we learned about the force of gravity, both universal gravity and the force of gravity if we know the field of a planet. And what's going to happen is you're going to find the force of gravity, you're going to plug it into force net, you're going to determine the acceleration of the object, and then you're going to use it with the motion equations that we learned at the beginning of the year. So if you could start out today by drawing yourself a planet with some kind of object, like a baseball or an apple, that we're then going to drop toward the planet's surface. This object will have only one force acting on it, and that will be the force of gravity. So we're going to start out and say, if we know the gravitational field, we use this. If we don't know the gravitational field of the planet, we'd use this one. Since this is on Earth, we're just going to plug in 9.8 times the mass of the apple. We could ignore this one altogether. We then take that force, and since there's only one force on the object, we put that force in as our force net. We divide by the mass of the object, and that will give us the acceleration of this object as it falls toward the ground. Once we do that, we plug that answer into our list of 5 possible variables, and then we look for other things, such as the height that we're dropping it from, the initial speed when it left my hand. Then we can figure out things like how hard is it going to hit the ground? How much time is it going to take to fall? Okay, so that's one example. And then once we have 3, we could find the things that we do not know. So again, this encompasses all the things we've learned so far this year. So let's try it for a 2-kilogram object on Earth. Take the 2 kilograms, put it in here, multiply by 9.8. You'll get 19.6 newtons pulling down on that apple. Take that 19.6, put it in as the force net, again because there are no other forces acting on the apple once it leaves my hand. Divide by the mass of the moving object, which is the apple, and get your acceleration of the apple. And when you do that, you will get an answer of 9.8 meters per second. Not coincidentally, the same number we had for our gravitational field. Why did it work out this way? Will it always work out this way? Let's take a look. On the first step, we took the mass of the object and multiplied by the gravitational field. And in the second step, we divided by that exact same mass. We multiply by a certain number, we divide by the same number. Those two numbers are going to cancel out. So it leads us to a super important conclusion. The mass of the object does not affect the rate at which it falls. Let me say it again. The mass of the object does not affect the rate at which it falls. So if I was to drop a baseball and a tennis ball that have 2 totally different masses, they should fall side by side. They should fall at the same rate. And on our planet, they fall at the rate of 9.8, the same as our gravitational field. Now the units are meters per second. That answer would go down here, and we actually make it negative because the acceleration is happening downward toward the center of the Earth in the negative y direction. Doesn't mean it's slowing down necessarily, because in this case it's speeding it up, but it's speeding it up in the downward direction. Okay, again, we need to know some other things. So if I just let go of the ball, it had an initial speed of 0. And if I knew how high I dropped it from, I could put that in there also. Remember, if I drop it from 5 meters, it's going to go down 5 meters. So I want to make sure I make my delta y negative. It got lower by 5 meters as it fell. All right, and then I would work through and I could solve for how much time it takes to fall and how fast it's going when it hits the ground. I just wanted to show you a quick video. Keep this in mind because on Wednesday I'm going to ask you to create your own version of this. I want it to be great. I want it to be brilliant. Mine is okay, but I think you can do something a little more creative. Okay? I'd like you to show me and make sure you record it in super slow-mo. I'd like you to show me as these objects fall, that 2 objects with a different mass will fall and hit the ground at almost exactly the same time. I say almost because you have to make sure you let go of them at the exact same millisecond, and that's going to be pretty hard. So I dropped a shot put and a field hockey ball, and you can see they both fell side by side. Mass of the object does not affect the rate at which it falls. We can see this on a graph. If we plot mass versus fall time, you can see it turns out to be a no relationship graph. The mass has no effect on the time it takes the object to fall. Realize there will be some experimental error. You might not always drop it from the same height. You might be off when you do your timing. But if you watch it in super slow-mo, you can see that mass has no effect on fall time. Realize, just like with every scientific model, there are limitations to the model. And the important limitation you want to understand is this idea is only true when gravity is the only force acting on the object. Which means if there is air resistance, that is going to change this idea that mass does not affect free fall. So for objects that are very light, where air resistance may dominate, or for objects that are moving very, very, very fast, where air resistance is going to start slowing them down, this will not apply. But for most objects falling over a small distance, this model works beautifully. Okay, you can see the field hockey ball and the shot put, this model works beautifully. Now, if I had dropped these from a helicopter, they may not have stayed side by side the whole way down, because at some point they're going to be affected by air resistance, and the field hockey ball being lighter will be affected before the shot put is. All right, so remember the limitations of your model. Okay, this was discovered by Galileo Galilei, very important discovery. So add him to your important scientists. So far we've done Newton, and now we see Galileo. He was from 1564 to 1642, so he had a nice long life. We could see he was from Pisa, and that was part of the Duchy of Florence. Nowadays we'd say he was from Italy, but Italy did not exist as a country back then. So it's more accurate to say he came from Pisa. And although we don't know if he did this, it seems logical that he would have tried to drop his objects from the highest available perch. And that highest available perch could have been, for him, the Leaning Tower of Pisa. Okay? So if we imagine Galileo dropping 2 objects with a different mass, side by side, he would have seen that these 2 objects stayed together, so long as they were heavy enough to overcome air resistance, and that the mass would not affect the time of fall. Obviously, if he dropped something that air affected, this would not be true. Okay, let's drop a super ball and watch it in slow motion, and then let's track it as it falls, and you can see the position of the super ball every 30th of a second. And what you should learn from this is that the super ball got farther and farther each time, not in a linear fashion, but in an accelerating fashion. We already talked about the fact that it accelerates at 9.8, but I want you to see exactly what that means. It means that each moment it falls, it covers a greater and greater distance. You can see early on it's barely moving at all, and by the end it's moving very, very fast. And in fact, it will follow this pattern. More time gives it a greater speed. You drop your phone, the more time it's fallen, the faster it's going to be moving when it hits the ground. Okay? If you drop it and don't push it, it will have a starting speed of 0. And you'll see the slope will be 9.8 on the planet Earth. It gains 9.8 meters per second every second that it falls. If instead you applied position versus time, you would see the change in speed evidenced by a change in the slope of the graph. The final thing I'd like you to learn is an idea called terminal velocity. We talked about eventually how air resistance will start to affect the object. Terminal velocity occurs when the gravity pulling the object down is perfectly balanced by the force of air resistance trying to stop it from moving. When these two are equal, the force net will be 0 and the object will stop accelerating. At that moment, it will no longer gain speed and will have reached what's called terminal velocity. We're not going to get into exactly how to calculate it because it is kind of more difficult than a first year course would typically have. But the terminal velocity depends on things like the shape, like the surface area that's cutting through the air, like the density of the air. Okay, like the material that it's made out of. And also the mass of the object. All of these things will help come together to determine the maximum speed the object can have, the point at which it will no longer gain speed. Okay, terminal velocity. Here are the terminal velocities for certain objects. Please take them with a grain of salt. You'll notice with humans I list the terminal velocity of about 53 meters per second, which is a little bit over 100 miles an hour. That doesn't mean if we drop all humans out of an airplane with parachutes before the chute opens that they'll hit 100. It depends on how heavy the person is, how they arrange their body, okay, a little bit what clothing they're wearing, okay, how wide they are. And this is kind of like the highest terminal velocity that most humans would achieve when they jump out of an airplane. Obviously, when the parachute opens, it's going to have a much lower terminal velocity. So this is pre-parachute. You'll notice a bullet is about 90 meters per second, which is around 200 miles an hour. And the interesting thing about that is when a bullet comes out of the gun, it's going way faster than that. Which means if you were to shoot a bullet straight down out of a helicopter, the bullet would actually slow down as it fell. Although gravity is pulling it down, the air resistance would be stronger than gravity, and the bullet would hit the ground at only 200 miles an hour, much slower than it left the gun. Oftentimes you'll hear people talk about dropping a penny off of a very tall building, and they imagine it slicing right through the skull. Well, that's not going to happen because the penny's going to top out at around 45 miles an hour. Fast, but not fast enough to do permanent damage. A baseball, somewhere around 90 miles an hour, which means a human can throw a baseball faster than gravity could pull it to the earth. Even if dropped from a very high height, it's still not going to reach the speed that a human could achieve by throwing it toward home plate. Finally, an iPhone, and again, take it with a grain of salt because it depends on how the iPhone is oriented, but maybe around 35 miles an hour, which means dropping an iPhone from higher and higher heights At some point, it doesn't matter how high it is because it can't get any faster than about 15 meters per second. So when you see someone doing things like dropping a phone with a special case out of a helicopter, you think, man, that's really impressive. It's really not that impressive because it's similar to dropping the phone from just a few stories up. The phone is not going to be able to accelerate forever. So adding extra height does not make it more dangerous. So again, I would not recommend dropping your phone out of the helicopter. But if you did, it would accelerate on the way down. But at some point, it would hit a terminal velocity. And then it would no longer matter how high you dropped it from. Okay, so I'd like you to just try one problem for me to make sure you can actually put this into practice. So this is from The Good Place. And in this scene, one of the actors is almost killed by a falling air conditioner. And I'd like to see if you could figure out how high the air conditioner was when it was dropped. And it's not going to have been so high that it hit terminal velocity. An air conditioner is a very, very, very heavy object. It's going to have a pretty high terminal velocity. And in this case, it only got up to about 11 meters per second, way below terminal velocity. Okay, so here's Chidi on his phone. He jumps back because of Michael, and down comes the air conditioner. So luckily, he was not in the path of that air conditioner. So what you do is you make your list, delta Y, VI, VF, A, and T. Because we are on Earth, we use negative 9.8 meters per second. You don't have to go through the first couple steps on Earth because we know the answer already is going to be negative 9.8. Doesn't matter how heavy the air conditioner is. It's just important that the air resistance hasn't stopped it from accelerating yet. Okay, when it reaches the ground, it was going 11 meters per second. And we make that negative because it was heading downward, not upward when it hit the ground. And when it left the window, we could assume it just fell out of the window and somebody didn't actually throw it down trying to hit him. That it was just they opened up the window and out went the air conditioner. Okay, so with those three things, see if you can figure out how high and how much time it took for the air conditioner to fall. And that's where we're going to stop for today.